All right, so here we go. We have a kind of continuation on what we did live yesterday. And this is going to talk about mean and standard deviation of discrete random variables. And then we're going to talk about continuous random variables in a bit as well. So we had mentioned this yesterday, but the expected value of a discrete random variable is calculated as follows. And we'll take for an example, we'll put an example up here. We'll use, 0, 1, 2, and 3. And we'll do 0 is 0.002, 1 is 0.029, 2 is 0.132, 3 is, hold on 1 second, sorry. Lost my data. Three is going to be, let me spread this out a little bit. 3 is going to be 0.309. 4 is going to be 0.36. And 5 is going to be 0.168. Okay, I'm going to take this for our example. So an expected value of a discrete random variable is calculated as follows. We write it down as e of x, sometimes ex, sometimes ex, sometimes ex, and sometimes mu of x, or just mu. All of these are equivalent. These all mean the exact same thing. We like this one, and we like these two mostly, but all of them mean the same. And it's really pretty easy. We take the sum, we add up all the values of my random variable multiplied by the probability that my random variable achieves that value. All right. So in our case, for our example above, we would get 0 times 0.002 plus 1 times 0.029 plus 2 times 0.132 plus 3 times 0.309 plus 4 times 0.36 plus 5 times 0.168. And if we were to do that, we would get that we are equal to 3.5. All right. Pretty easy. All right, we look at the columns, right? We take this column, gives us this term. This column 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 gives us this term. I guess this column gives us that term. Then we just add them all together. Standard deviation, a little more complicated. So first we do variance. Variance of a discrete random variable x, we can write as the sum, and we're going to take our xi's, we're going to subtract our expected value, and we're going to multiply by our probability. Okay, so we take our values, we subtract our expected value, and we square this thing. Forgot to square it. and then we multiply by our probabilities. So in our case here, our expected value is 3.5. So we're going to get 0 minus 3.5 squared times 0.002. And then we're going to add 1 minus 0.35 minus 3.5, excuse me. 3.5 squared multiplied by 0.029 plus 2 minus 3.5 squared times 0.132 plus 3 minus 3.5 squared times 0.309 plus 4 minus 3.5 squared times 0.36 plus 5 minus 3.5 squared times 0.168. And this works out to 1.05. And that's our variance. This is our variance. Right? And our variance we often denote as sigma squared. So our standard deviation, which I guess I'll do down here in pink, standard deviation, which I'll write in pink, is the square root of variance, which is the square root of sigma squared, which we just write as sigma, which is going to be equal to the square root of 1.05, which is 1.02. So there's our standard deviation of our discrete random variable. Okay. We're going to use the calculator. We can use the calculator to calculate these. I will include a video linked to the assignment to show you how to do that. But some notes on the AP exam. If you have to calculate some of these in a free response problem, you have to write out what you're doing. But you can do it with ... dots. So for instance, if I was to solve this problem here, if I wanted to find the standard deviation for some reason, I would write sigma squared is equal to, say 0 minus 3.5 squared times 0.002 plus 1 minus 3.5 squared times 0.029 plus ... plus 5 minus 3.5 squared times 0.168. Right, so you can write it out like that, and then you just give the answer from the calculator, right? And then you could say this is equal to, I said 1.05, so this is 1.02. All right, so you just give the answers from the calculator, but you do have to write down what you are calculating. All right, and then we'll talk about continuous random variables. A continuous random variable takes on any number in an interval on the number line. So for example 1, let's let y equal a randomly generated number between 11 and 23. Randomly generated number between 11 and 23. So what's the probability that y is equal to, say, 24.6? And here's an important thing about continuous random variables. For a continuous random variable, if you want to know what is the probability that you take on any specific value, it's always 0. All right, it's always 0. And what continuous random variables care about really is ranges, right? So we can actually answer what's the probability that y, say that, I don't want 24.6. I want, I read that wrong, 14.6, right? The probability that I'm equal to any specific value is always 0. Say, for instance, what's the probability I'm between 12 is less than or equal to y is less than or equal to 15. Well, this one we can actually calculate. And the way we do it is we figure out how big this interval is. This interval has size 3, right? 15 minus 12 is 3. How big the total interval is? Well, it's 23 minus 11, that's 12. So this is 1/4. All right, so there's one way of doing this. All right, and this randomly generated number, we assume it's like uniformly random, right? A probability distribution of a continuous random variable is always defined by a density curve. We need a curve for finding areas. This is always how this works. Let's write down the density curve that describes example 1. So we're going from 11 to 23. It's a uniform density curve. It doesn't tell us anything about any kind of distribution. It's a uniform density curve. So what height is it at? Well, this guy has length 12. It's a rectangle, and our density curves always have area 1, so this has height 1/12. All right? And if I wanted to actually do 12 to 15, we can do, here's 12, here's 15. We just want to figure out what's the area of this rectangle. Well, it has height 1/12. It has width 3, so the area of this rectangle is 3/12. Or 1/4, just like above. We always have a density curve for a continuous random variable. And we have to actually kind of have a little bit of a note of caution here. For any continuous random variable, like I said before, the probability that my random variable is equal to just a number. So let's say probability that y is equal to just, we'll use a. This is always 0 for a continuous random variable. And the other word of caution we have to worry about, the probability that a less than or equal to y less than or equal to b versus the probability that a is less than y is less than or equal to b versus the probability that a less than or equal to y less than b. And I guess also the probability that a is less than y is less than b. I think those are all possibilities. These are all actually equal. So we can't tell endpoints apart. Which is okay. Doesn't really matter. The important fact is that it is continuous. All right. So what I want you to do for problems, I want you to do example 2 here. Example 2. It's a uniform density curve. Another example is we have a normal distribution here. Normal distribution. I didn't write it down, but we want one. Normal distribution. Right? So normal distributions are examples of continuous random variables. I should do problem 1 here as well. And in the textbook, in section 6.1, I want you to do problems 1 to 10 and 24 to 30. They should all be pretty quick. I know it seems like a lot, but they should all be pretty quick. All right, guys. Good luck.